Okay, Assalamualaikum and good morning. So today we try to focus on the dynamic behavior of higher order system. So previously we already covered the first order where the power of the S is equal to 1, and then based on the yesterday example, the interacting tank, we already covered the second order system where you have the S power of 2. So what happens if you have a power of 3? So that become the third order. And if you have S power of 4, then it become fourth order. So if you have the system with more than 2, power of 2, then we classify it under the higher order system. Usually, the first order can be obtained when you have the single unit operation. For example, you have the CSTR when you try to develop the overall mass balance, component or energy balance. In the end, after the Laplace transform, you will get the transfer function in the form of the first order. So the second order usually can be obtained when you have two multiple tank. Two tank in series, for example, the interacting or non-interacting. So however, it is not common to have a first and second order in the system. In the chemical industry, usually you have a multiple unit operation. That means you have more than one unit operation. So this, if we take into account the overall balance for the whole overall process, then it becomes more than one order. So usually for this part, we have two class of higher order system, where the first one could be in the n first order in series. So this means you have the first tank, you develop the first order, and then this tank connected to with another tank. Then if we take into account two tanks in series, it becomes second order. If you connect the second tank with the third tank, then if we take the overall balance, then it becomes the higher order. And the higher order also can be obtained based on the process with the dead time. Dead time means you have the time delay. Of course, usually if we take the reading from the unit operation, the reading usually not spontaneously. For example, if you want to take the temperature at the distillation column, usually the reading is connected by the electrical instrumentation. For temperature reading, usually we use thermocouple. So this thermocouple is connected to the distillation column. So if we try to measure the temperature inside the distillation column, then the measurement takes place into the distillation column. It will transmit into the piping line, the electrical line into the thermocouple into our monitor. So by that time, we have sometimes a delay, sometimes maybe 1 second or 2 seconds. So this combined with the transfer function of the distillation column, it becomes the higher order system. Let's revisit the non-interacting case study, where in order to develop the mathematical model for the given tank, usually we will do part by part. So we focus on from the left to the right. So in this case, we focus on the tank number 1. We develop the overall mass balance. So after we do the Laplace transform, in the end you will get the first order transfer function, K1 over tau 1 S plus 1. Subsequently, you will focus on the tank number 2. Do the same derivation. You will get the first order transfer function for the tank number 2. So meaning that this one is a separate cases. We do part by part. So you do the mathematical model, you will get the first order. You do the second tank, you get the first order. If we try to take it overall, then that means you will multiply the G1 and the G2. So what happen, if you multiply G1 and the G2, you will get in the form of the second order process. So let's consider the three-tank non-interacting system like as shown in the figure 1. So you have the tank number 1, you have the input coming into the tank number 1, and then is exit to the valve, and then after the valve you have fed the flow rate into the tank number 2, and then subsequently you have the second valve, and then it flow to the tank number 3, and finally you have the exit valve from the tank number 3. So meaning that if we want to develop the overall mass balance, we will do from the tank number 1, tank number 2, tank number 2. We develop separately. We didn't do simultaneously. So of course, based on the previous example, this one you will get the first order. And if you do the tank number 2, you will get another first order. And lastly, for the tank number 3, you will get another first order. So if you want to take it overall, then you will multiply the first order for the tank number 1, the first order for the tank number 2, and the first order for the tank number 3. So this, if you do the multiplication, you will have tau 1s, tau 2s, tau 3s. So it becomes s power of 3. So you have the third order system. So usually this third order system is identified as the higher order system. So this is the formula to obtain the overall transfer function based on the non-interacting tank, where you will have to multiply the transfer function for each available tank. Let's say if you have 3 tanks, so that means you multiply the transfer function for the tank number 1, multiply with the tank number 2 and tank number 3. So you will get the overall transfer function for the given process. Of course, the transfer function will become more complex because you have additional power of the S, and usually you will have the characteristic of the overdamped system. And if you have a lot of the tank, then usually the response becomes sluggish. So what is sluggish? Usually here, if you have the graph, this is like overdamped system. Overdamped system is okay because it keep increasing and then it will become reaching the steady state by the end of the operation. But the sluggish means sometimes you can have the response like this. So this means it become increase, and then the oscillation become bigger. So that's what we call it sluggish. So it's not smooth. Sluggish is the opposite of the smooth. The smooth graph, you have the increment steadily until it reach the final steady state. Sluggish, you have some minor oscillation or bigger oscillation. Okay, another way to obtain the higher order transfer function is when we try to combine the process with the dead time. So usually the dead time, sometimes we call it as the time delay. So the delay for the response to be measured. This delay can be sometimes based on the situation where you have the slow fluid flow in the pipe. Of course, if we connect the first tank and the second tank, we connect with the piping. this piping connect the tank 1 and the tank 2. We cannot estimate that, oh, after the tank 1 exit, the flow will flow in quickly to the tank number 2. There will be some delay because of the friction, because of the viscosity of the liquid, which is make it the fluid to resist the flow. So this is classified as the time delay. And sometimes, for example, the delay can be occur based on the transport of the solid material. For example, using the conveyor belt. Of course, when we try to move the solids by using the conveyor belt, it will be moved slowly. What happens if we try to increase the speed of the conveyor belt? Then that's mean maybe the solid sometimes is not in order. Maybe it will be taking out from the conveyor belt. So we will move the solid sample slowly. This slow movement resulting into the time delay. And of course, the most common time delay obtained in the chemical process is when we try to do the chemical analysis. So sometimes for the temperature, usually the time delay is very small because the reading can be taken quickly. If we have the time delay, usually 1 second or 2 seconds. The same goes with the level. If you want to measure the level, we can read the level quickly from the given unit operation. For example, if you have the kettle to boil the water, you have the scale outside the kettle. So that means if we put the water into the kettle, we can read the level quickly without time delay. It's a real, what we call it, online reading. How about if we want to measure the composition inside the tank? This usually we have a big time delay because usually you have to take the sample from the tank. You do the analysis by using the gas chromatography of the HPLC, high pressure liquid. So this is considered as the time delay. So here is the process with the dead time or the time delay. The time delay usually occur between the input and the output. We start with the input xt. Any input, this input can be the inlet flow rate, can be the inlet temperature, and then you have the box of the process. It's not necessarily the first order, it can be second order or the or the third order. It depends on the type of the process. So based on this process, then you have the output. So if you don't have the time delay, then this is your final transfer function. If you have a time delay, so you have to include the that time here, where the time delay usually based on the, let's say, 1 second or 2 second, is represented by the TD, or sometimes we call it theta D, time delay. Depends on the definition. So here the dead time is, that's mean usually if you have the response, the first order response, you start from the time equal to 0. But for the time delay, you have the delay of the output. So that means you will start maybe a little bit later. So this is known as the time delay. You have the same response, only you start slower because of the delay of the response. So based on the block diagram, if you try to do the Laplace transformation, let's say for the first order process, you have the k over tau s plus 1, and then the time delay represented by the exponent negative tds, where if we have the combination of this one, then it become first order plus time delay. FOPTD, first order plus time delay. If you have a second order process, it becomes second order plus time delay, SOPTD. So for the process with the time, without the time delay, this is your transfer function. And for the dead time, usually this is the transfer function for the time delay, exponent negative TDS. And if we try to combine both, you just multiply the box, the first order transfer function and the dead time, and it becomes this. This is what we call it first order plus time delay. FOPTD, first order plus time delay. So although the original transfer function in the first order, when you try to combine it with the dead time, it is classified under the higher order system because you have another s here. Here you have the exponent power of the s. So this is the response for the process with the dead time. Of course, when you have the input, you don't have any delay. So your input start with at the time at t equal to 0. And then based on the time delay, your output response will start later based on your time delay. So it didn't start at 0. It will based on the how long your time delay for the given response. If you have the time delay equal to 2 seconds, then that means your process start after 2 seconds. Although your input already start at time equal to 0, but due to time delay, your response can be read after 2 seconds. So this is known as the process with the dead time. So of course, when we have we obtain the transfer function for the given process, either the first order or second order, the next step involved with the inverse Laplace. So we try to transform the S Laplace into the time domain in order to solve the problem. So for the first order or second order, usually we can refer to this table, where based on this we find what is our transfer function, and then we obtain the time domain for the given inverse Laplace. For example, the first order, this one. So you can obtain this transfer function, this time domain function. So based on this, you just take the equation, then you try to solve the given problem. But for the higher order, usually it's not available based on the table 3.1 here. So it's a little bit complicated to do the inverse Laplace for the higher order. So how we can inverse Laplace the higher order? That is the main question. So in practice, if we have the first order response, then we can do the inverse Laplace based on the table 3.1 or appendix A3. Second order, also you have the inverse Laplace. But for the higher order, based on the undergraduate study, we did not recommend to do the inverse Laplace directly. It become complicated. So what we can do is try to do the approximation of higher order transfer function. The approximation means we try to simplify the higher order of the transfer function into the first or second order. So how to do the simplification? So in order to reduce the number of higher order or the higher order into the simple order transfer function, we can use what we call it Padder approximation. So here, through the Padder approximation rules, if you have the exponent negative TDS, it can be converted into the common transfer function equal to 1 minus TD over 2S divided by 1 plus TD over 2S, where your time delay here, you divide by 2. For example, if you have exponent negative 2S, where the 2 is your time delay, let's say 2 seconds. So this can be converted into the common transfer function by using first order approximation. 1 minus TD is 2 divided by 2, so 2 over 2 is 1, so 1 minus S divided by 1 plus S. So in this way, you no longer have the exponent, so it becomes the normal transfer function. So in our practice, usually we just focus on the first order approximation because we want to make it simple. So we just use the first order. Of course, we have another form which is the second order approximation. However, here you have the S power of 2, so still it is complicated. So this one usually we did not cover. We just focus on the first order approximation. Usually, why we don't want this that time as the exponent, because first it's very difficult to do the inverse Laplace, thus it's leading to the difficulty to solve the problem. And if we try to do the control on the time delay, then it becomes harder to maintain the operation at its set point, because the process become unpredictable. So another way to do the approximation of higher order transfer function is by using what we call it Taylor series approximation. So in this Taylor series, is much more simpler compared to the Pader approximation. In the Pader approximation, when you want to convert the time delay, you have the numerator and denominator. Exponent negative TDS equal to 1 minus TD over 2S divided by 1 minus TD over 2S, 1 plus TD over 2S. But for the Taylor series, it's much more direct, where you have exponent negative theta S equal to 1 minus theta S. Here you use the theta, sometimes you can use exponent negative TDS. It's a different symbol but have a same meaning. It depends on the textbook. Sometimes they use the theta, sometimes they use the TD. Both are the same thing. If you have the exponent negative 3s, then it becomes 1 minus 3s. So here it is much more simple compared to the Pader approximation. So sometimes they say if you have the Taylor series for the exponent negative theta s, sometimes you have theta s equal to 1 minus theta s. So that means here 1 minus theta s over 1. So this one is the numerator. If you want to make it sure you don't have any negative anymore, then the exponent theta f can be converted is by equal to 1 divided by exponent theta s, and then you approximate by 1 divided by 1 plus theta s. In this way, you transform the transfer function from the bottom to from the top to the bottom. It's up to you. Usually this one is much more favorable, because usually for the transfer function you have k tau s plus 1. For example, you have first order, you have 3 over 5s plus 1 exponent negative 5s, for example. So if you try to convert using this one, this become 3 1 minus 5s plus 1. So you have this term, the negative term. So the way, if you don't want to have the 1 minus 5s, then it become 3 5s plus 1, and then this one become 1 plus 5s. So indirectly you have a second order. So if you have a second order, then you can easily do the Laplace transform by referring to the appendix. So this one still in complex condition. So we usually favor the bottom part where we can be easily to do the inverse Laplace. So in the previous case, we already have the Pader approximation and the Taylor series. So based on this method, you can convert the time delay into the common transfer function. So from the E negative TDS equal to 1 plus theta S, for example. So how about if you have the fourth order? So you have K over tau S plus 1, tau S plus 1, tau S plus 1, tau S plus 1. So how this fourth order can be converted into the first or second order for ease of simplification. So what we can do is by applying the Skojestad half rule. So through this Skojestad half rule, we approximate the higher order model that contain multiple time constant or multiple tau S plus 1, and then here we try to reduce it from the higher order into the first order transfer function. Okay, through this half rule, it approximates the largest neglected time constant in the following manner. So that means the largest time constant here means that if you have the third order, so the third order you have K tau 1 S plus 1, tau 2 S plus 1, and tau 3 S plus 1. So here you have the third order. So here in this case, based on the Skojestad half rules, the largest neglected time constant in the following manner. So you have the 1/2 of its value is added to the existing time delay, and the other half is added to the largest retained time constant. So meaning that here you need to take into account the time constant given. One of the time constant will be divided by half, where the first half you add with the existing time delay if you have that, and the other half you add with the retained time constant, and the smaller or the neglected time constant is added into the time delay. So we take a look on the example. Based on this example, we consider the transfer function g equal to k negative 0.1 s plus 1 divided by 5s plus 1, 3s plus 1, 0.5 s plus 1. So in this case, you have the third order transfer function where you have the tau 1 is equal to 5, tau 2, tau 3, and another time delay here, another transfer function at the numerator. So this third order transfer function can be approximated through the first order plus time delay. So if we want to convert the higher order here into this kind of form, so the objective is to reduce this order into this form. So here the k still the same. It didn't change, but here you have the exponent negative theta s and tau s plus 1. This one, the original, you have 1, 2, 3 time constant. So how this 3 time constant can be changed into 1? So we try to apply two methods. First is the Taylor series expansion, and the other one is Skojestad half rule. So for the first method, now based on the Taylor series, the negative 0.1s plus 1, this is the numerator for the given equation. If we use the Taylor series, it becomes exponent negative 0.1s. By so in the previous example, you have three transfer function: 5s plus 1, 3s plus 1, and 0.5s plus 1. The largest time constant will remain at the denominator. So you remain the 5 at the bottom because this one is the largest time constant. So how about the other two? So the other two time constant, 3s plus 1 and 0.5s, can be converted into time delay. So 1 over 3s plus 1 is equivalent with the exponent negative 3s, and the 0.5 is equivalent with the negative 0.5s. So this is identified as the new time delay. So you add all of it, 3, 0.5 and 0.1, it become exponent negative 3.6, and the other one become 5s plus 1, where this one is the largest time constant. Why the largest time constant is remain? Because usually this will affecting the process very much. So because it is the dominant dominant time constant affecting the final response, so this will remain at the bottom. The other two, because the value is smaller than the 5, so this one, because it's less affecting, we convert it into the time delay. So the final transfer function is k exponent negative 3.6s and 5s plus 1. This transfer function is known as the first order plus dead time, where you have the first order and then the dead time. So how to apply the Skojestad half rule for reducing the higher order transfer function? So in this case, you have the original transfer function as the third order. So here our objective, we want to convert this into the G approximate as k exponent negative TDS over tau s plus 1. So the k still remain the same, no problem. So for this one, we don't, for the Skojestad half rule, this is not applied, so we have to convert this transfer function using the Taylor series approximation. So that's mean negative 0.1s plus 1 become the exponent negative 0.1s. So here you have 3 time delay. Tau 1 equal to 5. Tau 2 equal to 3. Tau 3 equal to 0.5. So by applying Skojestad half rule, it indicates that the higher transfer function, higher time constant is remain. So 5 is remain, and the half rule is applied on the second largest transfer function, which is in this case you have 5, 3, 0.5. So the second largest is this. So this value you need to divide by half. So that means you have 1.5 and 1.5. So what are we going to do with this half? So this first half you need to add with the largest time constant. So that means the 5 must be add with the 5 plus 1.5 become 6.5, and another half you add with the remaining or not use the time constant. So this become 1.5 plus 0.5. become 2. So this become your time delay TD, and this 6.5 become your tau. So here you have another time delay which is 0.1. So this is another time delay, so you need to add the post time delay. So that means this become k exponent 2 plus 0.1 become negative 2.1 s over 6.5 s plus 1. So this is your time first order plus time delay for using based on the Skojestad half rule. So this is the explanation to use the Skojestad method. So you have three value of time constant based on the half rule. Half of this value is added to the next largest time constant to generate a new time constant, which is phi is the largest time constant, and the second largest is 3. By dividing half you get 1.5, so 1.5 plus 5 you get 6.5. So the other half from the 3 is 1.5. We add with the additional time delay. The original is 0.1, so that's mean 1.6, and the other one is 0.5. So 1.6 plus 0.5 is 2.1. So this is your new time delay, and this is your new time constant. So in this case, the final transfer function first order plus time delay using the Skojestad half rule is shown here. K exponent negative 2.1 s divided by 6.5 s plus 1. So from the third order, we reduce to the first order plus time delay. And why we want to reduce? Because for ease of the solution. If we take a look, in this case, we have the response for the given process. Originally, if you take a look the actual one, the solid line, this is the original response for the third order transfer function. By solving it, we get like this. And then by using the Taylor series as approximation, by shown by the dashed line here, you get like this line. So this is the Taylor series. So because of the time delay, you have a slower response here. But in the end, the process approximately similar with the actual response. The same goes with the Skojestad method. In this case, you have little bit time delay. So the time delay obtained from the Skojestad better than the Taylor series. So it mimic the real actual response. So that's why in this case we want to reduce the order of transfer function become first or second, because for the ease of the solution, and in the end the response you will get is approximately similar. So previously we already covered the approximation of higher order transfer function. Now what I want to show you is the stability of the transfer function. So we start with the first order transfer function. Let's say for the first order you have the k over tau s plus 1. Okay, so for this is your transfer function, and then by using the step input, so you have 1 over s, the change is magnitude of 1, and this is your response, where for the first order typically it will steadily increase until it reach the steady state value, so it's maintained. So this is what is known as the stability, the ability to maintain the final value at the fixed point. So the first order usually is identified as the stable response. So for the second order response, usually for the second order, you have three classes depending on the damping coefficient. Either is overdamped, critically damped, or underdamped. So for the overdamped and the critically damped, the response is like the first order. So that means it will steadily increase and then it reach the final value. For the underdamped, you will have a response like this where your damping usually between 0, damping less than 1. The damping cannot be negative. So the value must be between 0 and 1. So for the second order, you will have the oscillation. Still, if you have the oscillation, we consider it as a stable because finally, if we prolong the time, it will reach the final value. It will reach the new steady state value. Still, we consider this one as the stable system. Although it is not favorable because you have the overshoot here. The good response is like the first order where you have the response steadily increase until it reach the final value without the overshoot. So here the process with the overshoot for like the underdamped response is not favorable. So let's say you have the third order and fourth order. How we can know the process is stable or not? So that's the question. So the one way to confirm is try to solve it. But in order to solve the higher order, it become problematic. It become complex. So how from the transfer function we can identify the stability of the response? So here we can use the what we call it the poles and zeros to identify either the response is stable or not. In this case, they say you have this transfer function, the higher order transfer function where you have the k, gain, and the time constant. Here you have the numerator and denominator. Usually the zeros is located as numerator and the poles is located as denominator. For example, like the first order, phi to s plus 1. So in this case, you don't have any s at the numerator. So that means you don't have any zeros. So no zeros. The zeros is applied when you have the s like this. And then here the poles based on the bottom part. Because you have the s plus 1 here. So 2s plus 1 equal to 0. So you find the root of the s become negative 1 over 2. So this is known as poles. Poles represent the root of the transfer function. So how to use these zeros and poles to identify the stability? It is based on the root. For example, like previous example, okay, you have phi to s plus 1. So in this one, you don't have any zeros because you don't have s. But the poles, you have 2s plus 1. So the s equal to negative 1 over 2. So this is your poles, the root of the equation. So negative 1 over 2. So you have a negative half, negative 1 over 2. The location of negative over 2 usually based on this axis is on this part. So negative 1 over 2, it become stable. So whenever you have the negative root, it become stable. If you have positive root, then it become unstable. Unstable is like this one. Why it become unstable? Because if you take a look, initially it becomes static, and then you have the oscillation, the rate of oscillation getting larger, resulting into the bigger sluggish response. and this one will never reach the steady state. The same goes with this one. You have the increment of the response, and then this one we may keep increasing. So this one is not stable, and this, like the over them, under them, although you have the oscillation but in the end it become steady. So this one is considered as stable, and this one of course is stable. So from the given response, if we have the poles negative value, then it becomes stable process, and if we have positive pole, then it become unstable. Okay, let's take a look on the example. Let's say you have a higher order response. You have 3 1 minus 2s divided by s plus 1, s plus 2, and then s plus 3. So in this case, for the zeros, you have 1 minus 2s. 1 minus 2s equal to 0. So your s will become 1 over 2. For the poles, you have 3 time constant here, s plus 1, s plus 2, s plus 3. So that means you have 3 poles. S plus 1 equal to negative 1. S plus 1 equal to 0, so S equal to negative 1. S plus 2 equal to 0, so S equal to negative 2. And then S plus 3, so S equal to negative 3. So here the 0 is not affecting much on the given response. So usually if we have negative or positive 0, it does not matter. The most important is the poles, the location of the poles. This will influence the final response. So in this case, you have negative 1, negative 2, negative 3. That means you have 3 poles at negative 1, negative 2, negative 3. So if we plot the location, you have negative 1 here, negative 2, negative 3. So negative 1, negative 2, negative 3. So that means it is under the negative axis. So this process in the end will reach like this. So it becomes stable response. Let's say another example. This value is negative. So when it is negative, so that means the 0 still remain the same, the s plus 1 remain the same, so this will be changed as negative 2. So the answer is s plus equal to 2. So that means your region, you don't have any this one anymore. So negative 1 is here, negative 3 is here, and then you have s2. So the position is here. So what is the expected response when you have one pole over here at the positive value and 2 at the negative value? So what is the response? It become like this. So first it becomes steady because of the pole, but in the end it becomes unsteady. So although you have one pole at the unstable region, in the end your process become unstable. We don't have any partially stable, either is stable or unstable. It does not matter if you have 4 or 5 pole at the negative region, as long as you have one at the unstable region, then in the end your process become unstable. For the zeros, it just indicate the how the response looks like, either it become slower or become quicker, so it's not affecting much. But the poles represent how your process or response looks like, stable or not stable. So finally, what I want to cover is the final value theorem. So in this final value theorem, of course, when you take a look on the transfer function, higher order transfer function is very difficult to do the inverse Laplace. So one of the way that we can solve the higher order, first we reduce from the higher to the first or second order, either using the Taylor, Scoggins-Stuart rule, or Pader approximation. Another way, if we want to estimate the final value of higher order transfer function, we can use what we call it final value theorem. So through this final value theorem, we can estimate what is the final value for the given transfer function. So here we use the limit, LIM is the limit yt at time infinity equal to limit sys. Sys here means you multiply s multiply with the ys. Ys is your transfer function. So s equal to 0. When the time infinity, s become 0. For example, let's say you have the ys here, 1 over tau s plus 1 multiply with the a over s, where the a over s here, sometimes we call it as the magnitude, m. Okay, so ys here, you multiply based on the formula. When the limit yt time equal to infinity, the limit s multiply with the ys. So s here multiply with the ys, so or you can multiply it here. So this will be cancelled. So you have the a multiply with the 1 over tau s plus 1. So you get a over tau s plus 1. So based on this, at time infinity, so that's mean if you want to find what is the y infinity, what is the value, so here s become 0. Time infinity, s become 0. So that's mean this one becomes 0. So 0 plus 1 is equal to 1. A divided by 1, you get a. So you have the final value of a. So let's take a look on the example of the final value theorem. Let's say I have y s over u s equal to 3 over 2s plus 1, 3s plus 1. So what is my y infinity? So previously we can do the inverse Laplace to solve this problem and put the value of the time equal to infinity and get the final value. Here by final value theorem, first we need to have the us. Let's say the us is given as 5 over s based on the step input. So that's mean your ys equal to 3 2s plus 1 and 3s plus 1 multiply with the 5s. So based on the final value theorem, y infinity is approximate to the limit s equal to 0. S multiply with the ys. So this means this equation is multiplied with the s. So when you multiply with the s, automatically this will be cancelled. So time infinity, s equal to 0, so this one becomes 0. So this means the answer will be 15. So without using the inverse Laplace, I can know the final value of the given equation is 15. So this can be applied for the first order, second order, higher order. If the question asks you to find what is the final value, or sometimes we call it ultimate value or new steady state value, all of this happen or occur at time equal to infinity. When it's occur at infinity, you can use final value theorem to find this value at time infinity. So the topic covered in the test is up to here. So this means if we cover from the beginning, the chapter 1, the transfer function for the first order, for the second order, for the higher order. When the first order you have normal mathematical model, you employ the Laplace transform to obtain the first order transfer function. The same goes with the second order. You obtain the second order, you do the inverse Laplace, you solve the problem. And the chapter and the higher order, you have either the need to use the Scott-Start half rule, Pader approximation, time delay, and then the final value theorem here. So this covered for the test 2 weeks later, 2 weeks in the future. So with that, thank you very much for your attention. So if you have any kind of question, you may contact me directly in the WhatsApp or so on. So best of luck. Thank you.